Welcome to my presentation. My name is Xu, and I'm an MPhil student at the University of Hong Kong. And my topic today is the applicative intersection types. It's a joint work with my supervisor, Bruno, and my collaborator, Ning Ning. All right. I will focus on four main points, which is I will give the introduction of the intersection type and merge operator. And second, I will show some applications of the merge operator can encode. And I will show you some challenge that how to design a simple system to include those features. And finally, I will give the overview of the key ideas of our work. And what is intersection type? It can be interpreted as a term E having a type A and B, which is an intersection type. Means E has both type A and B. It's originally introduced by Cooper. It allows some canonical forms in nominal calculus to be well typed. For example, we can give the intersection type to the type variable A, x, which is A to B and A. But later, the interpretation has been slightly adapted. In practical programming language like TypeScript and Scala, intersection types has been used to encode some features. For example, the multiple inheritance and the records. We can check the simple example of the TypeScript. Here, we define two interfaces, which is the name and ID. Both interface has only one attribute. And later, we can create a new type person, which is the intersection type of the name and ID. So in this definition, to build the inhabitant of the person type, we need to provide two values for the person, which is the value for the smaller ID and name. Our system actually uses a similar idea. We call it the merge operator. It's originally introduced by Jan Dunfield in elaborating intersection types and union types. It's interpreted as E1 merge E2. We use double comma as the merge operator. It can be used as the E1 and E2. The merge operator forces intersection types to be explicitly introduced and inhabited. We can check the typing rule for the merge. Here we use the bidirectional typing style. There are two modes of it, which is the check mode and the info mode. So the typing rule for the merge is that if E1 has type A and E2 has type B, then E1 merge E2 has intersection type, which is A and B. We will see that merge operator adds expressive power to language and enables many applications. All right, the first application is Extensible Records. Records can be represented by syntactic sugar of the merge operator. We can check the example of multi-field records, which is we have two fields, X, Y, Z, which is just three single-field records merged together. With this encoding, we can get the record subtyping for free. For the way subtyping for record, which basically is record with more fields, is smaller than record with less fields. And this subtyping rule is subsumed by the subtyping rule for the intersection types, which is A and B is smaller than A. And for the record projection, it's standard. We just create the merge term, which is multi-field record. We project this merge with the label X, and the E1 will be returned, which is the associated value of the X. And for the record concatenation, we simply merge more and more fields into the original field, which is add the new record in the multi-field record. All right, we can take a look at the second application, which is the overload function. The overload function basically says function implementation is dependent on the types of arguments. We can consider the example of Haskell. It has a show function. The type of show is a polymorphic type A to a string, and this polymorphic type A is constrained by a show type class. Here we provide two instances for the show class, which is showInt and showBool. And with this definition, instance will be selected automatically according to the argument type. Here, we can apply our overloaded function show to an integer 1. The show int will be automatically selected, and we will return a string 1. And this is also the same for the show true. So in a system with merge operator and intersection types, we can define it, just merge two implementations together with the show int and the show bool. So the type of show function is basically the intersection type of two implementations, which is a string into string and bool string. And for the overloaded application, it's very standard. We just apply the show function to integer 1, and show int is automatically selected. We will return the string 1. To add a new instance to the overloaded function, we just simply by merging, we can define a new show function by just show merge with a new instance, which is show double. And the third application, we call it the return type overloading. It's a slightly different with the overloaded function, since the function implementation is dependent on the surrounding context instead of the arguments. We can consider Haskell's read function. The read function type is a string to a polymorphic type A, and the polymorphic type A is constrained by a read type class. Here we provide two instances for the read function, and which is reint and rebool. So instances will be selected according to the surrounding context. Here, we have the successor function, which expects an int argument. So the int argument is the surrounding context. And we apply the successor function to the read string 1. The reint will be automatically selected, and we will get the result integer 2. And with the Calculi with merge operator, we can do a similar one. We can define our read function by merge, reint, and rebool. The last application is relatively new. We call it nested combination. It reflects the distributivity of intersection types at the term level. Here, we provide two rules. The first rule is basically the intersection types can distribute over the record type. The second rule is that intersection types can distribute over the function type. So the nested combination, simply speaking, is that results extracted from the nested terms will be composed when eliminating terms created by the merge operator. We can check some examples. For records, we have X associated with E1 and X associated with E2. We project this record with the label X. The E1 will be returned and E2 will be returned. We compose them with the merge operator. And for the overloaded function, we first define f. F is int, and G is into bool to bool. We then create the overloaded function by f merge G. So we then create this overloaded function to integer 1. Since f and g both expect an integer at the first argument, so it cannot determine which instance to be selected. So the result is basically we parallelly apply the f to the integer 1 and g to the integer 1, and then we compose them using the merge operator. You may already notice that both cases seem unnatural, since we allow the repeated labels and ambiguous over the application. But however, it has been proved the nested combination has many good parts. For the nested record project combination, it's a key feature of the computational programming, which is a new programming style that solves the expression problem naturally, and it models forms of family polymorphism. And for the nested function combination, it enables we call the first-class curried overloading. And in this definition, the overloaded function are default curried, and we can abstract return the overloaded function in a flexible way. It's a novel and interesting finding in this work. So since we already covered 4 applications of the merge operator CAN model, so what's the challenge of designing a simple system to support them? The challenge has been split into two parts, which is statistics and dynamics. Because in traditional calculi, we have the following typing rule for the application. Here, to infer the application term E1, E2, and we first infer the E1. The E1 has a function type A to B. And we use the input type A to check the arguments. And we use the output type B to use it as the inference type of the application term. But however, in a system with merge operator and intersection types, this rule cannot apply to the case. It's because our E1 can be an intersection type. We cannot simply extract the input type out of the intersection type to check the arguments, and we cannot simply get the output type to use it as the inference type of the application term. And we may have some brainstorming. The direct method is to make two assumptions, which is we assume we have the argument type A, and we assume the type of function is an intersection of function types, which is A to B, A to B, and A to B style. And then we iterate these intersection types by comparing the argument type A and input type A. And then we compose the outputs as a result type. We can reuse the same idea in the dynamic semantics, which is we make assumption that overload function is a merge of functions. And we select them according to the argument types. This implies that we adopt a call by value strategy, and our operational semantics is type dependent. However, even we may make some assumptions, we have the final challenge, which is distributivity of intersection types, breaks the assumptions. Here we can see the example, create a function pshow. Pshow is a function, simple function, that is a show function wrapped with a func. So the type of pshow is unit to the type of the show function. In this definition, the pshow is still an overload function. We can apply pshow to the unit and the integer 1. And the correct instances will be automatically selected, and we will get the string 1. We apply pshow to the unit and boolean true. We will get the string true. In this definition, pshow is not a merge of functions. However, instead, it's a lambda. And its type is not an intersection of function types. It's just a function type, but it's still treated as an overload function. So we can move on to key ideas, how to solve the challenge. The first tool we can seek help from is the subtyping. Here, we may have the A is a subtype of B to C. Here we suppose A and B, A, B, C are given. We can tell whether the following subtyping holds, which is int string and bold string is smaller than int string. It tells us some information that because the first side is the type of the show function, and the right side is the type of the show int. So this subtyping can tell us that show int is one branch of the overloaded show function. We can slightly reinterpret the subtyping by omitting the output type C, which is we suppose A and B are given, and we want to infer the result type C, which is basically int string and bold string is smaller than into question mark. Here, the left side is basically the type of the overload function show, and the integer int is argument type. We are basically want to infer the output type C here, which is also the type of overload application. And we then design a specialized form of subtyping. We call it the applicative subtyping, which is smaller than the selector type A's. We use it to infer the type of applications and projections. We have 6 rules. The first two rules deal with the function. If A is a function type and we got the argument B, we're simply comparing whether B is a subtype of A1. If it is, we return the output type A2. If it's not, we return a failure. And the 3 and 4 deals with the record case. We simply compare whether their label are equal. If it is, we return the associated type A. If it's not, we return failure. For the intersection type, we distribute the select type A's to two branches, which is A and A1 and A2. And we compose their results using a special composition operator. And we can see the example how to use our applicative subtyping to deal with our overloaded application. For the show one, we got the type of the show function, which is int string and bold string, and we got the argument, which is integer. We then distribute the argument type to each branch, which is int string, and we computed with the int, and we got bold string, which computed with the int. Because the first branch succeeds, we just got the output type string. The second branch fails, we got a failure. And we can continue to look at the read string one. The first branch succeeds, and we got the integer. And the second branch also succeeds, we got bool. We just compose them results. We can continue unfolding our composition operators. We just show one version that implements, let's say, composition semantics. We also have another version which models the overloading semantics. So for the let's say composition semantics, if both branch fails, we fail. If only one branch succeeds, we just use the results from that branch. If both branches succeed, we combine them using the intersection type constructor, which is A1 and A2. We can recheck our example by unfolding the composition operators, which is we got a int string and bold string, we got argument integer, we got a string. And for the read function, we got a string, our inference type would be an int and bool. And for the record, we got a label y, and we can fetch the result type, which is string. And our applicative subtyping is used in a typing rule. Here we slightly modify the original typing rule in the bidirectional typing style. We infer both the function type and the argument type, and we compute out the type C, which is the result type of the application term. And with this definition, with the applicative subtyping, with the composition operators, and with the new rule, we can make some inference of the application. The f function is already mentioned. It's int to int, and g is int to bool. We first create an overload function f and g. We apply it to the integer 2 and the boolean true. We first infer the overload function, which is int to int and int to bool. And we start to analyze the argument, which is 2. The type of it is an int. We start our first computation, which got our result int to int and bool to bool. We second analyze the true, which is bool. We start computing, and we got our result type, which is a bool. So the bool type is basically the result type of this application term. All right, with this definition, since our implementation and definition is inspired from the subtyping, so it should have the strong correspondence to the original subtyping. The first three lines is basically the results of our algorithms. And the below part is the subtyping rule for the normal subtyping. We can see that it should have the strong, sound, and complete property of it. So we can further prove that our applicative subtyping is sound and complete to the normal subtyping, which is if A and the argument B, we compute out the type C, then A is smaller than B to C. For the completeness lemma, if we have the subtyping case A is smaller than B to C, then we can always compute it a result type D, and D is a subtype of C. And to deal with the operational semantics, we can slightly design the canonical forms of our language, where where our values can carry extra annotation. And the extra annotation is considered as the runtime types here. And our dispatching technique is based on such runtime types. And we also make a small restriction on the runtime type, which settles as the canonical form of the overload function, which deals with the distributivity. We can take a look at a small portion of our operational semantics, where we have two rows. After we reduce all the function and the record and argument to the canonical forms, we just call them using our special dispatching judgment. All right, our dispatching judgment, we call it the applicative dispatching. The idea is very simple. The first two rules is basically deals with the beta reduction and projection. The last three rules deal with the dispatching. The intuition is basically we extract the output, the runtime types out of the value, and we use this runtime type to compute. Here we can see the example here. We can picture v1 as a function and v2 as an overload function, and we create an overload function. And VL is the argument here. This we extract out of the runtime type out of the v2, and we extract the runtime type out of the VL. If it fails, we just use the result, which is v1 applied to VL. We got the E here, which is the result of the overload application E. And if both succeeds, we just got the E1 and E2. We compose them using the merge operator. And in this definition, we can have the standard type soundness, which is basically held by the standard preservation and progress. And that's basically all my talk. We can have more in the paper, which is sounds and complete lemmas in the setting of records. And we have different variants of sound and complete lemmas with regard to the difference of typing. And we can have the second calculus, which has some disjoint restriction, and it's proved to be subsound and deterministic. We also have a racket interpreter implementation of the calculi. You can basically check the calc formalization and the interpreter implementation using this link. Thank you. That's all.
Thank you. Any questions?
Yes.
All right.
Hello. Do you really need the records? Like, if you can define any singleton type, then you can use the way you concatenate functions to encode your concatenated records. So
Sure, exactly. Because in the original paper of Castagna, for the overloaded function, he also used the function to model the record. But this record here, we have the explicit type record type. And if we just model the records using functions, we kind of lose the type system out of the record type, right? And the record type here is basically used to model some kind of features in object-oriented programming, like traits. And that's the reason why we need to keep the record here.
So you are typing the record differently with respect to how will you type the function encoding suggested by Castagna.
Exactly.
Thanks. Have you thought about compilation? So
Compilation?
So compiling this down into some binary, because then you're going to have to keep those tags at the front line, and that might incur some additional costs. So I guess the question is, have you thought about the overhead of keeping those tags?
I see. Because we can also have the elaboration semantics, which is basically models the compilation. But the reason why we adopt the operational semantics here is we want to have the direct proof of the type soundness. Because in the original paper of Jenna Dunfield, she basically adopted elaboration semantics, which models, but the type soundness is very hard to prove. And that's why we want to modify it using the operational semantics. But simply speaking, for the implementation, it's totally fine to use the elaboration semantics.
you mentioned runtime types and use in runtime dispatching. Is that necessary, or is it possible to determine the type of everything statically?
Yeah, I think it's possibly okay to dispatch basically all the stuff statically because this is overloading. It's not the method. But it's again, since we have the operational semantics, that's why we need to use the runtime types. If we adopt another semantics like elaboration, then all the things like dispatching can be done in the static way.
Okay, thank you very much.
So you showed some example uses of your system to type classes. So how general is this? Can you use this to include any kind of type classes, including hierarchical classes?
Yeah, because actually we compared with the type class in Haskell, we lack out some ability. We call the resolution. It's like we use the list type constructor, and we got another overload function. So it's basically hard to remove. Like for the Haskell, we have the list type, and yes, I will talk later because I kind of forgot there. But compared with type classes, we only lack the ability of the resolution.
So my question is, you mentioned that the problem of the traditional type checking, rule does not work because now the function can actually have an intersection type, which has some branches of functions. And I think an intuitive way to solve that might be just split this intersection type into several function types. And then you try, okay, can we use this function type in type check? Can we use the other one, right? And then you merge the result. Maybe there are some merge of the resulting types. So is this kind of approach? So what is the difference between this kind of approach and your approach?
It's like, do you just mean this one? We assume a type of function is an intersection of function types, and we then iterate each function type.
I think that is the
So the problem here, actually, this technique has been used by frankly in the refinement intersection types, but here we have the extra distributivity rule, and in this way we cannot assume a function must be an intersection of function types. We need somehow normalize the type into. If using your technique, we need to make some normalization to convert such a function type, the type of function, into a list of an intersection of function types. So the problem here is we have the distributivity, so we cannot assume it's the intersection of function types.
So I have a little question just about like you mentioned overloading, and then looking at the roots, it seems to matter. Like for example, if you have two functions that are overloaded but both have exactly the same type and they're merged, does it matter which one comes first?
That's we call the less accommodation. We just apply both functions to the argument, and then we compose their results using the merge operator, and you basically got the two results merged together. For example, if it's a successor and a predecessor, and apply to a 1, we will got a 2 merge 0. And it's basically caused some problem with the non-determinism, and we solve it in the second calculus, which we make sure the calculus is deterministic. We add the disjoint restriction, so the argument with the same type does not happen in the second calculus. Okay.
Would there be a way to have the non-determinism, but like remember what the pairs are? You think that would be useful? Like for example, instead of just having like merging the results, merging the input-output pairs or something like that.
Yeah, for the current part, since theory, the determinism is a very technical problem, and even in the second calculus, we still have some drawbacks, which is we reject some useful programs. So it's a future work to basically include all useful cases, and we want to retain the determinism property. All right.
Thank you.
Thank you.